Okay, welcome to lecture. We'll get started in just a minute. Again, we should be picking up on chapter 9 where we left off on Monday. And again, a reminder, if you have questions, feel free to type them in. We'll get to your questions and all that good stuff. All right, so when we last left, we got into chapter 9 where we're talking about really stoichiometry. Stoichiometry, again, is really conversion factor problems. They're conversion factor problems that actually use an equation. So we use the equation. And remember, as we talked about last time, and we'll talk about here again, it does need to be balanced. So it's really important that when you do any type of stoichiometry problem, that the first thing you always want to make sure is that that equation is balanced. Again, none of the sort of calculations will work properly if that equation is not first balanced by putting those coefficients in front of those numbers to make sure everything's good. Yeah, in terms of some of those experiments there, they were graded. They'll be uploaded shortly. I'm just going to wait until I'm finished grading the exams and everything. And then I'll upload all your current grades for all that type of stuff. I just haven't had a chance to upload those, but they have been graded from before we went online and stuff like that. So since I have the exam to grade and all that, you'll get a grade update fairly soon, including the one that you submitted last week, which I think was experiment 14. That's been graded as well. So you'll have an update very soon on those. But I do have them, and I did grade them. All right, so so when we're talking about stoichiometry, again, we want to use those equations as really conversion factors. So instead of sort of going to a table to look up a conversion factor like 1 inch is 2.54 centimeters, we actually use the actual equation to come up with some conversion factors. And we did some examples last time of that, and we'll look at it again here today as well. But when we do these stoichiometry steps, there basically is several steps that you want to follow. And what you see on the screen is kind of the steps to follow. If you happen to be given everything in words in terms of what's reacting, you want to make sure, again, as we talked about, you want to write the right formulas first for the reactants and products. You then want to balance the equation with the coefficients. Once you balance the equations, you want to convert whatever they gave you into moles. And usually a lot of times you'll be given the information in grams. So you want to take the grams using the molar mass to convert to moles. And that'll give you the moles of whatever quantity, either a reactant or product that you're started with. Once you do that, then you want to come to the stoichiometry step, which is right here, which is go to the balanced equation. And you're going to use those coefficients as a way to basically figure out the mole to mole relationship between everybody. And then lastly, once you do that, you'll be in moles, and you want to convert to whatever unit they want at the very last step there, step number 5, for example. And you want to make sure that you convert it. If they want grams, you may have to use the molar mass on the back end of the calculation. If they want some other unit like pounds, you may have to do several types of conversions on the back end. But a lot of the stoichiometry problems are really still the same, like 4 basic steps. A lot of times you're starting here with make sure that the equation is balanced. So you want to make sure that equation, right, is balanced that you have for that chemical reaction. This is usually the next thing that she has to do is convert grams to moles. So again, a lot of times it's in grams and you have to convert it to moles. Again, from the periodic table, the molar mass, that is basically what you're going to use to do that conversion. By the way, if they happen to be in some other units besides grams to begin with, you need to take those units to grams and then go from grams to moles at this point. Again, when you get to this step, you're going to go to the balanced equation. And you're going to use these coefficients that you have in front of everybody to come up with the mole to mole relationship. So for example, if I was interested in A, that'd be 2 moles of A from the actual coefficient equals 4 moles of C if I was interested in C. And as we talked about last time, using that relationship that you could get from the balanced equation, you could come up with 2 conversion factors. Again, you could say that there's 2 moles of A over 4 moles of C, are 4 moles of C over 2 moles of A. So we're going to use one of those sort of conversion factors that you could get from the actual equation. And the reason we need to do that, and that really is the stoichiometry part, is because, say, for example, in this little guy here, that we were given information about A to start with. So we were given information about this guy, but we're interested in coming over here to C. So we need a way to do that. And what's going to allow us to do that is the stoichiometry. So using that relationship. So stoichiometry is sort of a big name, but it really is just a conversion factor that allows you to go from one thing in the balanced equation to somewhere else in the balanced equation in terms of going from reactants to products. You could also go from products to reactants relationship. You could stay on the reactant side and figure out the relationship between 2 reactants. You could also say on the product side, if you had more than one product, you could figure out the relationship between those. And then really so that's usually the third step that you need to do. And then really the fourth step that you need to do is whenever you're done with this step, you will always be in units of moles. So usually you need to convert those moles to whatever units the problem wants you to do. So very commonly, grams is a very common unit. And again, usually, you'll have to use something like molar mass to go from moles to grams. So a lot of it is sort of the same basic 4 steps, just making sure that you follow them in order. If something is done for you, you could just skip that step, obviously, and go to the next step along the way. And that's something people sometimes do weird. They like undo things. So if something is already given to you in moles, you pretty much can skip this step here, right? And you can just go to the next step. You don't have to unconvert it and then reconvert it. All right, so let's take a look here. So for example, if we looked at another sort of equation, such as what we have here up on the screen, and basically here from this equation, we could figure out several relationships. And again, using the coefficients that are in front. So from this one, we could say for every 2 moles of CO, we get 1 mole of O2 that needs to be put in there. And again, no calculation to figure that out. It is just from that balanced equation. So that's where we're essentially getting those numbers from. We could also say for every 2 moles of CO, we would produce 2 moles of CO2. And we could also say from this one, for every 1 mole of O2, we would get, as we can see there from the product side, we would get 2 moles of CO2. So these are the 3 stoichiometric relationships that we could get from this actual equation. And from this equation, because of those 3, we can essentially write conversion factors for each of those. And to write the conversion factors for each of those, again, you could do, for this one here on top, you could do 2 moles of CO over 1 mole of O2. Or you could use it in the opposite way, 1 mole of O2 is 2 moles of CO. For our second one, we could write 2 moles of CO on top, gives us 2 moles of CO2, and 2 moles of CO2 on top, for example, would give us 2 moles of CO. Yeah, so those equations they're specific, obviously, for the. So the question is, I think, do those relationships change? They don't change, but they are specific for a specific balanced equation. If that's sort of your question, Grace, they do come from the balanced equation. So for every balanced equation, you could come up with a bunch of different sort of conversion factors, but it does depend on the balanced equation you're looking at as to perhaps how many you can come up with. And obviously the numbers would change based on the coefficients in that specific balanced equation. Other questions or that? Okay. So the what we have here from this one equation is essentially 6 different conversion factors that you could get from this one equation. And usually in a problem, you would not obviously use all 6 of them together. It would just be like a normal conversion factor. You would want to pick the one that would help you basically figure out what you're trying to solve for. So for example, if we started with, let's say we started with 25 grams of O2, and we want to know how many grams of CO would we need. We can kind of go through all of our steps to do this type of problem. So for example, I'm just moving some boxes out of my way here so I can actually see the screen myself. So the first step would be in any type of stoichiometry problem is basically a balanced equation. And obviously we do have a balanced equation here to begin with. The next thing that we want to do is take whatever they gave us, which in this case is 25 grams of O2, and we want to convert it to moles. So to convert our 25 grams of O2, we would need to go to the periodic table and look up O, right, oxygen, which is 16 grams per mole. And we would want to take the 25 and divide it by the molar mass of O2, which would be 2 times 16, which is 32. So we would then take the molar mass from the periodic table, which would be 32 grams per mole of O2. And we take 25 divided by 32, and that would get us something like 0.78, I won't round yet, to 5 moles of O2. Now, that's really your second step when you do these type of problems. And you can see that although we did a conversion, we're still at O2. And we have still only really converted the units from grams to moles. And that's problematic in this case because we're actually interested in CO. So we need a way to go from O2 to CO. And that is where the stoichiometry part comes into play. So if we take our number that we just got there, which is 0.78125 moles of O2, this is the stoichiometry part where we want to go to the balanced equation and we want to look at the relationship between the two things we're interested in. One thing we're interested in is what we started with, which is right here. And the other thing we're interested in is the CO in this case, which is what we're trying to find. And that would give us this relationship that we talked about just a second ago. And from that relationship, again, we could get these 2 conversion factors. And we would want to use it like a conversion. So really we have moles of O2 on top. So we would want to use the conversion factor here on the left to get rid of the O2. So we're going to get 2 moles of CO on top and 1 mole of O2 on the bottom. That is the big stoichiometry step there. That is going to cancel out the moles of O2, and we will end up with a number of 1.5625. Again, I'm not rounding yet. Moles of CO. Just going to put a little line between all that. Any questions on that so far? So that is kind of the stoichiometry part of the calculation. But in this case, another important thing is we're not looking for moles at the end. We're actually looking for grams. So that's going to require us to go back to the periodic table now that we're in moles, and go back to the periodic table and figure out the molar mass of CO, because that's where we're at right now. And again, that'd be 12.01 from the periodic table, plus 16 from the periodic table for the oxygen. And that's going to give us a molar mass of 2801 grams per mole. Yeah, so like normal, Grace, I'm going to try not to round to the very end, and then we'll kind of clean up the answer at the very end. So, we're not just off a little bit because of the rounding. So again, you don't want to round too strongly in between these steps, because again, you may end up with a number that's quite different than what the answer may be. So at this point, what we would do is the final step here, which is 1.5625 moles of CO. We're going to use the molar mass from the periodic table that we just calculated. We're going to want the grams on top. That's going to get rid of the moles. And we will end up with, grab a calculator here, 1.5625. And it looks like we will end up with 43.765 grams of CO. And now to answer your question, Grace, the only number that we had to start with was 25, which is 2 sig figs. So this probably should round to 2 significant figures, and something like 44 grams of CO would be the answer in that particular case. Any questions on any of those sort of steps? That is a basic kind of simple stoichiometry problem. Now, if you look at it, and what you'll see as we go through some more examples here, really a basic stoichiometry problem, it's all the same steps. You first want to make sure you got a balanced equation. You then want to take whatever they gave you and convert it into moles. You then want to go to the equation and do that mole to mole relationship. And lastly, because you will always be in moles at this point, you want to take those moles and convert to whatever units they want. In this case, we were looking for grams, so we use the molar mass. Like I said, you may need to use something like, some other conversions if they wanted maybe pounds or, whatever type of unit they may want. And really, stoichiometry really is these 4 basic steps. Any questions on that? Now, just so we're clear as well, you don't have to do it you don't have to do the calculation part kind of step by step and get an answer. You can just do it in one sort of big calculation where you just put all the steps together and just get the answer at the end. That's perfectly fine. So much like a normal kind of conversion problem, if you want to think about it that way, you could either do it kind of step by step like I just did there on the board and get an answer after each part of the calculation, or you can just kind of combo all those calculations together and just do it in one big calculation, obviously showing all the steps there, and you could get the same answer. What that basically means is in this reaction, if we threw 25 grams of O2, we would also have to put in there basically 44 grams of CO to get this reaction to sort of occur correctly. Any questions on any of those sort of steps? Okay, so let's take a look at some here, I think. So it's just going to fill in everything that I kind of scribble on the screen. And again, you could go back and see this if you want, but pretty much is everything we just did there on the last screen. Okay, So why don't you give this a try? Why don't you try the first part here first? We want to know lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of H2 can be formed by the reaction of 5.32 moles of lithium with water? So for this one, don't do the second part yet. We'll do it next. So don't worry about this one. So just start on the first one up to that first question mark. So do that problem up to that first one. So take a moment or two and see what you come up with, and then we'll talk about how to do it. Make sure everybody's on the same page. Okay, so let's take a look and see how we're doing. So when you see a stoichiometry problem, again, you want to follow those kind of four basic steps. So the first thing that all problems need is an equation. So in this case, we had everything that was given to us in words. So we want to make sure that we write the correct formulas first. So lithium metal would be Li. Again, it would have no charge because it's by itself and not combined with anything. Reacts with water, which is H2O, and it will form hydrogen gas. So a reminder that hydrogen gas is those diatomic molecule. So how it comes naturally is H2, and then it will form lithium hydroxide. So this is when lithium would get a charge of +1, and it would combine with hydroxide, which is -1, to give us LiOH. Any questions on sort of those formulas? And remember that it's important to write the formulas correctly first, and then you want to go back and balance. So in this case, to balance it, we need some coefficients. I think we perhaps need a 2 there, maybe a 2 there. Just putting 2's up. Let's see how we did there. And a 2 right there, I think. And that should give us, again, 4 hydrogens on each side. So we got 2 on the left times 2, which is 4. And then we got 2 hydrogens on the right and 2 more into lithium hydroxide, and 2 oxygens on the right, 2 on the left, and 2 lithiums as well. So that's the first thing. Remember that if you are given the equation in a balanced equation, or if you're given an equation with the formulas there, you should make sure you take a moment just to make sure that it is balanced. Probably if you see coefficients written down, it's probably going to be balanced, but just in case you don't see any numbers, you should make sure that it is. The next thing we want to do is take whatever they gave us, which in this case is 5.32 moles of, I believe, lithium, if I'm not mistaken. Double check there just to make sure. I got a box in the way. There it is. And we're interested in basically how many moles of H2 we could form. So in this case, the next thing that we want to do really is convert whatever they gave us into moles. So this is a case like I was talking about before. Obviously, it's in moles, so you don't have to undo it. It's already good to go. So that means the next thing that we want to do is basically the mole to mole relationship. And we want to look at the two things we're interested in. So in this case, one thing we're interested is the lithium, and we're trying to find the H2. So from the actual equation, we can see the coefficient says there are 2 moles of lithium, gives us 1 mole of H2. And again, this doesn't, no math involved there. It's just as simply the numbers that are in front of each of those formulas. And again, as we talked about before, and again, you don't have to write all these conversion factors down, but you can get 2 conversion factors from it. You get 2 moles of lithium over 1 mole of H2, or again, you could use it in the opposite fashion as 1 mole of H2 gives you 2 moles of lithium. So again, these conversion factors are coming from the equation, and that's going to allow us really to do the third step here, which is go from what we're not interested in this case, which is lithium, to what we are interested in, which is H2. So in this particular case, we would want to use the conversion factor over here on the right. So we're going to put 2 moles of lithium on the bottom and 1 mole of H2 on top. And again, this is what's going to be the big stoichiometry part. The 2 moles of lithium will cancel out with our mole of lithium over there. We're going to take 5.32 divided by 2, gives us 2.66 moles of H2. Now, in this particular case, we are looking for moles, which means step 4, we do not have to do. And step 4 is basically convert those guys into like grams or something like that. So in this particular case, this should be our answer. We started with 3 sig figs, we ended with 3 sig figs here, and we would get 2.66 moles of H2. Any questions on any of those steps? Again, you can do it all together in one calculation, which there's just one calculation in this case. And basically what this means is if you threw into this reaction 5.32 moles of lithium and everything went perfect, there was no side reactions, you weren't a klutz and spilled anything on the floor. Hopefully that wouldn't happen either. But you will be able to produce 2.66 moles of H2. Any questions on any of those steps there? Okay, so let's take a look at the second part of this problem, which I think, and again, all this is just what we just did. So I'll scroll it up there so in case you watch it again later, you can kind of see it all typed out pretty, but it's essentially exactly what we just did. And that's good, got the same answer, so that's promising. So let's take a look then at pretty much the same problem, but we're going to do the second part of the problem, which is for this one, why don't you focus on this part of the problem? So give this a go. Let me give you some information that might help you. Lithium from the periodic table is 6.941 grams per mole. Oxygen is 16 grams per mole. And let's see, hydrogen is 1.008 grams per mole. So give this a go. We're looking in this case for how many grams of H2 we would produce if we started with this 81.75 grams of lithium doing the same reaction that we did before over here. So take a minute or two, give that a go, see what you come up with, and we'll talk about it. All right, so let's take a look, see how we're doing. So in this case, we're actually given grams of lithium, and we're looking for H2 as well. But in this case, we're also looking for grams of H2 when it's all said and done. So the first thing you want to do is obviously have an equation, which we already had done from the first step. So that's all good. Again, here, the only thing that was given to us was 81.75 grams of lithium. So the next thing you want to do is take whatever they gave you and convert them into moles. Again, we would go to the periodic table to do that. And again, from the periodic table, we see that there are 6.941 grams per mole of lithium. And that's going to be our conversion factor to get rid of the grams. And again, you don't have to necessarily get an answer at this point, but if you did, it looks like you would have something like 11.7778. Again, I'm not rounding here until the end, moles of lithium. And again, that's a good step because that gets us into moles. And now we can do the next step, which is go to the equation and look at the two things we're interested in, which in this case, it happens to be the exact same thing as we did on the first problem. So just like in the first part of the problem, we see that for every 2 moles of lithium, we get out 1 mole of H2. So again, we're going to use that as a conversion factor because ultimately we're not interested in lithium. So the next part of the calculation we would do is actually the stoichiometry part. So since lithium's on top, we want to go 2 moles of lithium on the bottom and 1 mole of H2 from the top on top. And again, this comes from the balanced equation. Any questions on that? That then means if we do get an answer at this point, we're going to take that number we had previously and divide it by 2, and that's going to give us 5.8889. Again, not rounding at this point, moles of H2. And that's the stoichiometry part. That's the part that allows us to go from moles of one thing in the equation to moles of something else in the equation. And it really is just a conversion factor that allows us to do that. Any questions up until that point? I'm just going to rewrite that number down here. I missed an 8 there. Okay. So in this case, also different than the first one is the last unit that we're looking for in this case is grams. So we do have to do that last conversion, and we now going to go from moles to grams. Again, it's going to be the molar mass that's going to allow us to do that. And the important thing is we've now converted over to H2 in this problem, which means we want the molar mass of H2, which is 2 times 1.008, which is the molar mass of hydrogen. And that will give us a molar mass of 2.016 grams per mole. And that's what we're going to use here for the final part of the calculation. Here, the moles are going to go on the bottom so that they cancel. The grams are going to go on top. Again, the moles will cancel, and that will get us 11.87 grams of H2. That means that in this particular reaction, what that number means is if you did this reaction and you threw in there 81.75 grams of lithium, everything went perfect in this reaction, nothing bad happened, you should, in theory, produce 11.87 grams of H2 as a result of this reaction taking place. And that means that this number, which we'll see a little bit later on this chapter as well, is also sometimes what is referred to as the theoretical yield. And the theoretical yield is pretty much what it sounds like. It is based on the equation and that reaction, That is the maximum amount of product that you should be able to produce. Again, if everything went perfect in that case, nothing bad happened, nothing got dropped along the way, you know, you were paying attention as you're doing the experiment and everything went really good. You can hopefully see as well, it really is the same kind of 4 steps. I know I have more numbers to begin with, but really balance the equation, convert to moles, and try not to run over the box on my screen. Uh, do the mole to mole relationship, and lastly, convert those moles into whatever unit you may be looking for. Any questions on any of those steps? So if you just follow those steps kind of in order, balance the equation, convert to moles, mole to mole relationship, and then convert the moles at the end, you should be able to do any basic stoichiometry problem that you come across. Again, if something is done for you, one of those steps, you just continue to the next step. Any questions on any of that there on basic stoichiometry type problems? Okay. And again, it's just going to fill in all the stuff that I put up there. And I'll just scroll it through. So again, you can see it if you want to go back for my scribbly part. And it get the same answer, so that's good as well. Again, in this case, 4 significant figures there on the answer, because really the only number that we started with was 81.75, which is also 4 significant figures. All right, so you got one more here, I think. Why don't you give this a go for a couple minutes here and see what you come up with. Let me give you some numbers to use. Again, carbon is 12.01 on the periodic table. Oxygen is 16. And hydrogen is 1.008. All right, so take a couple minutes and see what you come up with here, and then we'll talk about it. So in this case, we're looking for the mass of CO2, so that basically means grams. So you're looking for really grams of CO2. Yeah. Okay, so again, this is a basic stoichiometry type problem. So you want to follow the same sort of steps. So first step is we want an equation and it's balanced. I see some numbers in here, so probably going to be balanced unless somebody's trying to trick us, which hopefully they're not. The next thing we want to do is take whatever they gave us, which in this case is 765 grams of the C6H12O, and we want to convert it into moles. And we do have to do it this time because, again, we're in grams, so we do have to convert it to moles. So that means that we do need the molar mass of our C6H12O. Again, that's going to come from the periodic table. That's going to be 6 times 1201 for our carbon, plus 12 times 1.008 for our hydrogen. And then we have 6 oxygens there. So that's going to be plus 6 times our 16 grams per mole. And that looks like you'll end up with something like 180.2 grams per mole as the molar mass of the C6H12O6. I left the O off of mine, or the 6 over here. Pop that back in. I don't know why I keep leaving that off each other. There you go. So we're going to use that as a conversion factor. So we're going to take our 765 grams of C6H12O6. And yeah, like normal, when we do molar mass from the periodic table, 4 sig figs is typically where we want to take the molar mass to. So whenever you pull any of those numbers off the periodic table for molar mass, 4 significant figures is what you're shooting for, which is why all these, if you look up here, are pretty much the 4 significant figures as well. So this is, again, the general rule that you sort of follow with molar mass. That 4 significant figures is sort of where you want to go. So we're going to use that as our conversion factor. So since we have grams, we want to put the grams on the bottom. That's 180.2 grams per mole of our C6H12O6. The grams are going to cancel. And if we get an answer at that point, we will end up with something like 4.245 moles of C6H12O6. Again, I didn't round too much here. I'm just taking it to a few digits. At this point, we're in moles of the C6H12O6, but again, we're not really interested in this guy. We are interested in our CO2. So this is where the stoichiometry comes into play. So from the equation, we can see that for every 1 mole of the C6H12O6, we produce 6 moles of the CO2. And again, no calculation there. It is simply just the coefficients that are in front of the formulas. So we're going to use that as a conversion factor. So we're going to take our answer from above, the 4.245 moles of C6H12O6. And again, here we want to get rid of it. So we're going to put it on the bottom. And from the equation, there is 1 mole of C6H12O6 gives us 6 moles of CO2. So this is the big stoichiometry part. That is what we're going to get rid of in this particular example, the C6H12O6. And that's going to allow us to get from there to our product, what we're interested in this case, which is CO2. So we're going to multiply that number by 6. And when we multiply it by 6, we end up with a number of 25.472 moles of CO2. So that was the stoichiometry part. Any questions up to that point? And again, I'm not rounding yet until the end. And also, like I mentioned before, you don't have to do it kind of step by step here. You can do one sort of big calculation. Any questions up until that point? So in this case, we are not looking for moles. So we do have to do that very last step, which is to convert our moles that we're in right now into grams. And to convert our moles into grams, we will need the molar mass. But the molar mass that we want to use here on the back part of the calculation is for CO2, because we have now converted into CO2. So if we go back to the periodic table, that's 12.01 grams per mole for our carbon, plus 2 times 16 grams per mole for our oxygen. And it looks like we get something like 4401 grams per mole, which would be the molar mass of CO2. So we're going to take our number here from above, 25.47 moles of CO2. We're going to multiply it by the molar mass, which is 4401 grams per mole of CO2. The moles of the CO2 will cancel, and the answer we get when we do this is 1121 grams of CO2. In this case, any questions on that first off? In terms of significant figures, the only number that we had to begin with was this number right here, and that is 3 sig figs, which means technically speaking, our answer here should become 1120 grams of CO2. Or again, you could write in scientific notation 1.12 times 10 to the 3. So that's another way you could write it. And that would give you, again, the right number of significant figures in this case. This, again, what this number means in this particular problem is if you threw in there 765 grams of the C6H12O6, everything went perfect. This is what is known as your theoretical yield. That is how much you should actually produce of CO2 in this particular reaction. Any questions on any of those steps, where we got the numbers, why we did any of those steps along the way? And you might be noticing a pattern. Again, it's really those 4 basic steps: balance the equation, convert to moles. Again, don't hit the little screen thing. Convert to moles. Do the mole to mole relationship from the equation, and convert moles to grams. Any questions on any of those steps there? So really, in basic stoichiometry problems, so you don't get lost along the way, I would just follow kind of those basic steps, and it should lead you to the path of getting the right answer. And like we talked about before, again, if something is done for you, don't go backwards, just go forward to the next step. And I'll scroll through this, which is everything we just did on the screen. And again, the part where I didn't scribble on, you'll be able to see later if you want to go back. And again, if you need something to put you to sleep, you can listen to this again, and we get the same answer. Again, any questions on basic stoichiometry type problems? So we're then going to kind of talk about really stoichiometry problems that are there's a little bit extra step involved that you have to do. And they're very common problems that you come across. And I'm going to actually skip this example here, but I'll scroll through it if you want to just see it later. It's basically the same thing we just did. It's just showing you could do it all in one big calculation. It's the same sort of steps that we just followed. I'll just put it up there for a second so you could look at it if you want later as well. All right. So the next thing we're going to talk about is about stoichiometry problems that involve limiting reagents. And basically what limiting reagents means is that in every reaction, there's usually a reactant that gets used up first. There's usually a reactant that will get used up before the other reactant, for example, and that is what is known as a limiting reagent. And some people will call it a limiting reactant as well. So sometimes you'll hear people refer to it as a limiting reactant. I personally will go with reagent most of the time, but sometimes people will call it a limiting reactant type problem as well. So that also means that there's usually a reagent or a reactant there that you have plenty of. And the one that you got plenty of and it's still there when the reaction's over is what is known as the excess reagent. So the limiting reagent gets used up first. The excess reagent you have plenty of is still there when the reaction's over. And what that means is why it's really important, the limiting reagent, is if you have a problem or reaction, say like this, and this is obviously your product, this is how much you're going to produce. And we'll just say that in this example here, A was our limiting reagent, B was our excess reagent. Actually, let me use a better symbol there. Go A and B together. So in order for this reaction to take place, we need A and B basically to come together. So why a limiting reagent is important is because once it's gone, you will no longer be able to produce product. So once you use up that limiting reagent, you no longer can produce any product, because in this example here, we need an A and we need a B. So as soon as A gets used up, there's no longer a way to put those guys together because we no longer have that A available to us. So the important part about a limiting reagent is it is the one that determines how much product you will make. So whenever you're trying to figure out how much product you should make in a reaction, which again is basically what we were talking about on the previous examples, that theoretical yield, it is the limiting reagent that is the one that will basically determine that for you. So you always want to use the limiting reagent to help you determine how much product you should make. The excess reagent will be there in a plentiful supply. It will still be there when the reaction's over. You got a ton of it. It's kind of like the old example. You go buy hot dogs, for example. I think they give you like 8 hot dogs, but you go buy hot dog buns, you get like 10 buns, or the opposite way around, one of those two. So, you're going to run out of hot dogs, for example, before you have buns runs out. So your buns are the excess in that particular case. So that's why the limiting reagent is really important. It is the one that basically will allow us to figure out how much product we can produce. Because again, as soon as it runs out, we no longer can produce products. Now, how do you know if it's a limiting reagent problem versus sort of a basic stoichiometry problem like we've been doing in the last few examples? The main way that you could recognize a limiting reagent problem is they will give you the starting amounts of at least 2 reactants. Yeah. So you'll get the starting amounts of 2 reactants. So if you look back at the examples that we did previously, the last couple examples or 2 or 3 examples, you were only given information about one substance in that chemical equation. You were given how much one of the reactants you started with, maybe you're given how much of the second reactant. But the way you can recognize that it is a limiting reagent problem is they will give you information that allows you to figure out the moles of each of the reactants. And basically, the steps to solve these are the same steps. You want a balanced equation. You want to convert to moles just like we did before. But if it is a limiting reagent problem, you need to do an additional step to figure out what is the limiting reagent, LR, limiting reagent. And we'll talk about how to do that in just a second. Then the rest of it is the same. Then you'll do the mole to mole relationship from the balanced equation. And then you will convert moles to some other unit. So a limiting reagent problem pretty much calculated the exact same way as we did the previous ones. The only additional sort of step that you need to do is right here. Somewhere along the way, you need to figure out which one is the limiting reagent. And that's important because that's the one that's going to determine how much product that you can make. Any questions on that? Okay, so as I mentioned before, the excess reagent, again, is the one that's there in excess, like the name implies. It means you got plenty of it. You won't run out of that particular one. So because you have plenty of it, you do not, again, you do not use the excess reagent to figure out how much product did you produce. You should always use the limiting reagent to figure out how much product that you will produce. So here's just a simple example here. We have female workout people, male workout people, and if we're going to put them together as workout buddies, we need one of each. We can see that we only have 3 guys here. So our guys in this case would be our limiting reagent. Our ladies over here will be our excess reagent because we got plenty of them. And obviously, the theoretical yield we could produce in this case would be only 3 sort of workout buddies, if you will. The other common question that we can answer when we do limiting reagent problems is how much of the excess reagent will remain. So we can actually figure that out, from doing calculations. And in this little example here with our workout people, we know that our excess reagent is our females over here. And we know that in order to make our product, we had to use 1, 2, and 3 of them. And that means that we started with 5 workout females and we only had to use 3. And that means that we would have 2 left over at the end of this reaction. So through calculation as well, and it's a very common question, you're oftentimes in these limiting reagent problems asked, how much product should you produce, which is your theoretical yield. And then it will also sometimes ask you how much of the excess reagent would be left over in this particular case. So obviously this is a simple example, a little bit more complicated sometimes with the calculation, but it's the same basic idea. Any questions on that there? Okay, so let's take a look here. So let's take a look at an example and sort of see how to do this. So actually, I'll just use, we got there, 4 and 20, right? So we'll use the numbers here, but I'll do it for. So we're going to say, for example, we started with 4 moles of the S and 20 moles of the F2. Okay. And again, we could recognize this as a limiting reagent problem because essentially what was given to us was the starting amounts. And we see that in this particular case, we're given the starting amounts of both reactants. So that is the trigger to tell you this is a limiting reagent problem. And that means that at some point in this problem, you need to figure out which of those guys is the limiting reagent. In this particular example, is it the sulfur or is it the fluorine? So the first thing you want to do is the same basic steps. You want to make sure you have a balanced equation, which we do. You then want to convert to moles, which in this particular case we don't need to do because it was already in moles. But just like in the previous problems, if they were in grams, you would need to use the molar mass to convert them into moles. So our starting amount is already in moles. So we started with 4 moles of sulfur, and we started with 3 moles, I'm sorry, 20 moles. 20 moles of F2. Okay. Now, once we do that balance equation, convert to moles, this is where we need to figure out which one is the limiting reagent. Now, to be truthfully honest with you, there's like 3, 4 different ways you could do this. So I'm going to show you one way. Your book may show you a different way, or if you look up somewhere online, you may see a third way. There's actually 3, 4 different sort of ways you could do these type of problems. But we're going to do it this way, and hopefully it will work good for us. So to do a limiting reagent, or to try to figure out which one is the limiting reagent, one way that you could do it is you can figure out how much of the second reactant is needed to use up all of the first reactant. So one way you could do this is just a basic stoichiometry problem where you pick one of these reactants, either the sulfur or the fluorine in this case, and you're going to do a basic problem that says, so for example, I'm going to take the sulfur and try to figure out how much F2 is needed. So if I start with my 4 moles of sulfur, from this equation, we could see that for every 1 mole of sulfur, we get 3 moles of F2. That's the stoichiometry relationship that we get from the equation. So using that, just like we did in the previous problems, we want to get rid of sulfur. So from the equation, we see 1 mole of sulfur gives us 3 moles of F2. The moles of sulfur will cancel. And this will tell us basically if we want to use up all of the 4 moles of sulfur we started with, we would need to put in there 12 moles of F2 is needed. First off, any questions on that little calculation there? Again, this calculation is going to help us decide which one is the limiting reagent. And basically what this calculation is saying, if I want to use up all of my starting amount of sulfur, this is basically how much fluorine I would have to put in there. Any questions on that? Yes, so Grace, we'll do the other one in just a second, but that's a good question. You can choose and do this type of calculation for either of the reactants. So in this case, you could do it for sulfur or for the fluorine. Now, once you do get the number, what you want to do is compare it to the starting amount of F2 that we started with in this problem. So we started with 20 moles of F2. We just figured out that we need 12 moles of the F2 to use up all of the sulfur. So it's a very simple thing to compare. Is 12 less than or more than 20? In this case, we have enough. So we do have enough F2. We need 12 moles. We're starting with 20 moles. And because we do have enough, what that means is our F2 would be our excess reagent. And that's important because by default, that means that the sulfur would have to be our limiting reagent. So if you could figure out one of those guys, which one is the limiting, which one is the excess, by default, the other guy has to be the excess. Yeah, so again, that's correct, Grace. You need, in this is pretty much what this calculation here is saying, that if I want to use up all of my starting amount of sulfur, which is basically what this is, right? I would need to throw in there 12 moles of my F2. And we want to go back to our starting amount in C for F2 that we started with 20 moles. And that means that we do have enough. And that would mean that the F2 in this example would be your excess. And by default, the sulfur would be your limiting reagent. Now, to answer your other question there, you can choose the other one. So you could do similar calculation to figure out how much sulfur you would need. And in this case, what we would do is we would start out with our 20 moles of F2. That again is our starting amount of F2, using the same relationship that we had up here, that 1 mole of sulfur is 3 moles of F2. We would do a similar little calculation. And in this case, the 3 moles of F2 would go on the bottom. The 1 mole of S would go on top. And we essentially take 20 divided by 3 gives us 6.67. And that gives us 6.67 moles of sulfur is needed in this case. And again, what that number would represent is how many moles of sulfur would be needed to use up the fluorine that we started with. So again, if you chose this calculation, when you're done, you would come back to your starting amount. And what you would see is we would need 6.67 moles of sulfur, but we only started with 4 moles, which tells us we do not have enough in this case. And it tells you the exact same thing as it told you in this calculation. Because we do not have enough, that would mean that sulfur would be our limiting reagent. And by default, the fluorine would be our excess reagent. So to answer your earlier question, you could choose either one. You could do this calculation like we did first, or you could do this calculation. It really does not matter which one that you choose. They both will give you the same answer in terms of which one is the limiting reagent and which one is the excess reagent. By the way, you don't have to do both of these calculations. You could just choose one, yeah? Choose one of these. And again, you could do either reactant. They both will basically tell you the same thing. Any questions on that part? So just to finish up this little part here, why this is really important is, as we talked about before, it is the limiting reagent that determines how much product you'll produce. So in a question like this, what we are looking to really figure out, for example, is how much of this product we would produce. So once we figure out the limiting reagent, the important thing is when you go to figure out how much product that you're going to produce, you want to go back and start your calculation with your starting amount. So you want to make sure you use the starting amount, not the number, for example, that you got down here. These calculations are just to determine which one's limiting. So now we're going to go back to our starting amount, and we would do 4 moles of sulfur. We would again go to the equation and find a relationship between sulfur and our SF6, which makes it a pretty simple one. It is a 1 mole of sulfur from the equation, gives us 1 mole of SF6. That will cancel out, and that would tell us that we would produce 4 moles of SF6 in this particular case. And if we want to know how many grams that would be, we would use the molar mass of SF6, which if I calculate it really quickly here, looks like it is 146.1. So we would take our 4 moles of SF6 and using the molar mass from the periodic table like we've done before, 146.1 grams per mole. Moles will cancel, and we would produce something about the right number of significant figures, like 584 grams of SF6 would be produced. And again, this would be what is known as our theoretical yield. Yeah. Any questions on any of those steps? So this is one way in which you can figure out the limiting reagent. You could do one of these 2 calculations. Again, you don't have to do both of these. You could just do one of these, either one. You can then use that to figure out how much or which one is the limiting reagent. Once you figure out which one's the limiting reagent, you then want to use the limiting reagent to figure out how much product you would make. Again, though, when you do that calculation, just like I just did, you want to make sure you go back to the starting amount for that limiting reagent and do the problem like normal. So it really is the same steps as what we did in the previous problems. It is still the same basic kind of 4 steps, but you do have to add that extra little step in the way. You do have step 1. This is our step number 2, which is converting to moles. And then our 3rd step to figure out the limiting reagent once we do mole to mole relationship, and then obviously calculating our products. Yeah. Any questions on that calculation? We'll talk about the lab in just a sec, Zach. Give me 1 second, and we'll talk all about that. Any questions on anything we talked about here today for lecture? Okay. A couple of things. The lab we're doing today is flame test, and I will post it here in just a second. So it will be available in a few minutes. As soon as we're done here, you'll be able to find it up online. Again, the flame test there'll be a link to a video where you can watch the video of a flame test done by somebody else. In that video, they do cover pretty much all the flame tests that you need to do in that particular experiment. So once you watch it, you can pretty much answer or fill out the rest of the report. There's one thing that I couldn't really find a video on, or they couldn't find a video on. It has to do with the cobalt glass. So what I'm going to do is, like normal, I'm going to open up the lab session in another meeting. And if you want to pop in up on the board, I'll be there to answer your questions, but I'll also probably up on the board have a little explanation about the cobalt glass part of the experiment. And that way you can kind of look at it and answer those questions and stuff like that. So in a few minutes, as soon as I'm done here, I'll make all that stuff available so you can see the experiment and then obviously there'll be a due date. This experiment, there's really no calculations or anything like that. I think it's just sort of observations and stuff like that. So it's a pretty quick one, I think. There will be an upload assignment for that as well, and a link in the module section. Again, you could link to it and then upload it. It is going to be due today since there's not much going on in that experiment there. So it will be due today. No, if I'm not mistaken, I think 15 is flame test. I don't think we did 15, or did we do 15? I don't think we did. I think it was on the schedule for. It was on the schedule for yesterday, I think, or regularly. So I don't think we got the flame test yet. Some of my classes did, but I don't think we actually did it. Even if we did it, we'll do it again. But I don't think we did. So that will be the experiment. So I don't think we did actually. So again, all that will be up in just a few minutes as soon as I'm done here. And like I said, I'm going to take a little break, probably like 10 minutes or so, and I'll open up the lab one where I'll try to put on the screen sort of an explanation about the cobalt plates that it asks about in the experiment, so you can answer those questions. Again, it will be due today. I think you got until, try to upload it when you're done. But I think you got a few hours or so to kind of upload it, and you'll be able to see that link to do that as well. In terms of the upload, most everybody seems to be doing okay on it. Just a couple of things. PDF is probably really good because I can see it, and when I grade these things online, I'm able to kind of put some markings on the paper, which I think once I post the grades, you'll be able to kind of open it up and take a look at, the markings and maybe what you missed and stuff like that. If you can't do the PDF and you have to do some type of photos, you can upload the photos individually, would be better than combining them all together in like a zip file or something like that. Because that way I can actually still be able to make some markings on sort of your papers and stuff like that. So you can kind of see when you look at them at the end, was my understanding, what you got kind of marked wrong for and stuff like that. But any other type of format I think is good. Just try not to do any type of zip file, because what that ends up meaning is I got to download it and I have no way to kind of put markings on it and stuff like that. So you won't be able to kind of see, kind of what you got wrong. You'll be able to see your score, but you won't be able to kind of see, what you got wrong or something like that. So that should be all good. I put the announcement up, and I think I answered most of your guys' emails about the exam. Again, I'm working through the exam. And just a reminder, I am going to go through not only the work that you uploaded, but I'm also going to go and look at all the answers that you submitted online as part of your answers. And again, anyone that the computer marked wrong because it didn't like the way you put it in. I know some of you use like subscript and superscript type of ways to do that. I didn't realize you had a way to do that from the entry part. So it definitely wouldn't have liked that when you did that, because it didn't have a way to kind of recognize it. So I am going to go back through, and obviously if I see that's the case, which on the few that I started grading, I did see that as sort of the case, I will adjust your scores and stuff like that accordingly. So again, that final score that you saw at the end probably is not going to be the same score that you'll end up with on the exam. I would think in most cases it should go up. It shouldn't go down, I don't think, but it should go up. I would think in pretty much all the cases. Or at worst stay the same for some reason, but it should probably go up a little bit once I do that. So don't worry if you did do something like that. I will sort of put that. I will put that together. So also, I think I took down the grades so you can't see them right now. So I didn't want you to keep getting notifications as I'm kind of grading them to bother you every 2 seconds. So they'll be back up there as soon as I'm done with them. So I think right now you might not even be able to see or access the grade part of it. I'm going to be a true honest with you. I think when it's graded, you'll be able to, if I'm not mistaken, I'm hoping so, but I think you'll be able to perhaps see it. Some of the feedback would be my guess. I know for sure on the you'll be able to see it on the part where you uploaded for the work. The multiple choice part and stuff like that, I'm not 100% sure you'll be able to access the feedback on that. But I think you might be able to, but you'll be able to see sort of the change in the score, I think, overall, for sure. But I know for sure when I'm done with the part that you uploaded, you should be able to see kind of the markings and stuff. And that's sort of where I'm putting all the markings on those type of problems. And in terms of the multiple choice, I'm not 100% sure, but I think you might be able to kind of see which ones you got wrong once the grade's been posted. So I won't promise 100% on that, but I think so. But like I said, on the written part and all that, you'll be able to definitely hopefully see the notes. Other questions on any of that? Okay, so like I said, I'm gonna go make the lab and all that kind of stuff available. I'm gonna start the lab meeting in probably about 10 minutes or so. And again, there's those questions about the cobalt glass. I'll try to scribble something on the screen so you can kind of look at it. You can pop in and take a look to hopefully answer those questions. And obviously, I'll be there for any questions that you may have, kind of through our normal lab time. All right, any other questions on anything else? Other than that, then we'll end the lab meeting. Have a good rest of your day. If I don't talk to you, or if you pop back in, I'll see you in lab. And again, we'll start lab in about 10 minutes or so. But I'm going to go make the lab links available right now. Other than that, have a good rest of your day. If I don't talk to you again, and I'll see you again next week on Monday. A reminder that today we're doing flame tests and all the rest of the labs have moved down a day or forward a day. All right, I'll see everybody in a bit.